This is 2007 AMC 10A Problem 21. A sphere is inscribed within a cube that has a surface area of 24 square meters. A second cube is then inscribed within the sphere. What is the surface area in square meters of the inner cube? So I've drawn the graph and I've split it into two parts. Firstly is the sphere inside the larger cube. Second is the smaller cube inside the sphere. So this cube is actually supposed to go into the sphere, but I've separated the graphs for labeling. So firstly, let's look at the first graph. So the first graph, so what information can we obtain? Well, it says this cube has a surface area of 24 square meters. So this is like the only number inside this problem. So it must be really important. But how is it important? Because we know that this is a cube, meaning that the side lengths are all the same. So this is S. If this is S, then everything else is also S. So like this is S, and that's also S, etc. Right? This means that the surface area is going to be 6 times one face, which is 6 times S squared, which is 24. This means that S squared is going to be 4. So S is going to be 2. So we know that the side length of this larger cube is 2. So that's kind of a bit of helpful information, because at least we have something to work with. So how does this help though? Because so essentially what happens here is that, so if I just move this graph down, if we look at this graph from a different view, for instance, let's look at this from the sphere's point of view. We know that the side length is 2, but let's just ignore that. We want to look at the sphere's point of view. So what's the radius of the sphere? The radius of the sphere is going to be from the center to, to this part. Yeah, to this part. So to any point on the sphere. So to this part. This is the radius R. Right? So what is R? We have to figure out R out from the sphere's point of view. So, however, the problem says that the sphere is tangent or inscribed inside the cube, meaning that this point actually touches. This point is a point that's on the sphere and the cube. So this, and also we know that this bottom point is also on both the sphere and the cube. So if we connect top and bottom points, this is the diameter of the sphere, and it's also the side length of the cube. So the side length of the cube is 2, and R is equal to S over 2, which is 1. So the radius of the sphere is 1. That's another piece of useful information. Let's move on to this graph down here. We know that the radius is 1, so let's draw the center. So before we label the radius, which radius should we draw? Well, we know that this cube, though it may not look like it, is actually inscribed inside. It's actually perfectly inscribed inside the sphere. This means that this point actually touches the sphere. This point also touches the sphere, etc. All the vertices touch the sphere. So let me just make this cube look more 3D. So like that, right? And then if we just connect this center point to all of the vertices above, and below the center, then these are all radii. So these are all radii because these points are all points that are on the sphere. So, but we don't need that much points. We only need one radii, or one radius, this one. So why this one? Because we can use the Pythagorean theorem. Essentially what the question is asking is what's the surface area of the inner cube. So we want the surface area of this, meaning we want the side length of this cube. For the side length of this cube, there's no other better way than using the Pythagorean theorem for what we know. We know this is the radius, which is 1. If this is 1, and if I did this, and this is perpendicular, this is the center of the square, of the bottom square of the cube, and I connected this center to this vertex again, then I have a right triangle. So let's look at this from another point of view. If we look at this from this bottom square's point of view, this is what we can see. We have a square. There's a center. There's the center of the square, and the center is connected to one vertex, to one vertex. So that's what we see. If we look at it from this right triangle's point of view, what we see is this. This is one. This is a right triangle, and yeah. So essentially, one thing we can obtain from here is if we name the side length x, so if I name the side length x, I know that this is actually x over 2, because from observation and also from drawing, we know that this is actually just half of our side length. If we connect the top and bottom squares, the center of the top and bottom squares, that is the whole side length x. So half of that is x over 2. So one side is x over 2. What about the other side? The other side is so this side is actually half of the diagonal of the square, right? It's half of the diagonal. What's half of the diagonal then? Half of the diagonal, so the whole diagonal is root 2x. So half of the diagonal is is x times root 2 over 2. So what does this mean? This basically means that by using the Pythagorean theorem, x squared over 4 plus 1/2 x squared, or x squared over 2, is equal to 1. So if we sum this together, or we multiply both sides of the equation by 4, we have x squared plus 2x squared is equal to 4, meaning that 3x squared is equal to 4. So x squared is 4 over 3. If x squared is 4 over 3, x is equal to 2 over root 3, which is 2 root 3 over 3. So if that's the case, the surface area is going to be 6x squared, because one side of the cube is x squared. So 6 sides is 6x squared. 6x squared is going to be equal to 6 times, so 2 root 3 over 3 squared is going to be 4 times, so 12 over, so it's going to be 6 times 12 over 9. So if we have 6 times 12 over 9, this gives us, 6 times 12 is 72 over 9, which is 8. So the answer to this problem is 8, which is C. So thanks for watching. Bye.